So now we have combinations, our next thing, which is actually much more useful. And the definition of a combination is basically choosing k objects from a collection of n objects where order does not matter. So we have a formula here. The number of combinations, which is choosing k objects from n, is n choose k equals n choose k equals n factorial over k factorial times n minus k factorial. So where do we get this formula? Well, we kind of notice that this part over here is just like npk. So maybe we can start there. So we note that if we have npk, and basically we have an order of k objects from n, and we can order them. For example, say k is 6 in this example. We could have 1, 2, 3, 4, 5, 6 as an order. We could also have 6, 1, 2, 3, 4, 5. And we could have different elements too. But the point I'm trying to make is that this one combination of 1, 2, 3, 4, 5, 6 gets recounted 6 factorial times, because there's 6 factorial different orderings of this from our permutation formula. Right? In general, if we have k objects, we're going to have k factorial times each thing. So what do? In order to compensate for this, we have to divide this by k factorial to get n choose k. Now, I say this is much more useful because it has applications in more than just counting objects. For example, it has a variety of uses in geometry. So we look at this example. So 11 points are designated on the plane. So you have to find the number of line segments with both endpoints among these 11 points. So in our example, rather than counting line segments, we notice that line segments have 2 endpoints, and these endpoints both have to be among the 11 points. So for every line segment, we can correspond with a pair of 2 points. So we're just choosing 2 points out of the 11. The number of line segments is just then 11 choose 2. And that's 11 factorial over 2 factorial times 11 minus 2 factorial, which is 9 factorial. After expanding everything out and simplifying, we can get that this is just 55. And that's our answer.